Good afternoon, everyone. Thank you, Gerard, for the introduction. As he said, my name is Tomas Mejia, and I am a second-year PhD student here at USP Pavia, and I will be talking today about some of the work that I've been developing during my time here in the Rhodes School, which is on the topic of understanding damage correlation in scenario-based seismic risk assessment. So, when performing regional seismic risk assessments, some modifications must be made to the standard PVEE procedure that is usually done for individual buildings, given that we are considering many structures that are located on many sites. So, for example, for the hazard, it is important to consider a spatial correlation. So when we calculate ground motion fields, they are realistic and they have realistic values. Another thing is that given that we're considering many structures, it would be pretty much impossible to perform a nonlinear time history analysis on all of them. We don't have generally nonlinear models of these structures, or at least enough information to do it. And even if we could, it will be very time demanding. So what is usually done is we group these structures into what are called taxonomies in a way that we consider like a representative behavior of all of them. So we use a common fragility function for all of them. We should also ask ourselves, we also needed to consider then some sort of damage correlation in the results, which is specifically what I'm going to be talking about today. So it is reasonable to believe that structures that were constructed in the same region probably share some characteristics in common in a way that they might have some strengths or deficiencies, common strengths or deficiencies. So for example, we can assume that there was a developer in a city that constructed many buildings. Probably the professionals involved in this construction of these buildings were the same. The building code use was the same. So as a consequence, if they made a mistake in the construction of one of these buildings, probably they also made that mistake in the construction of the other buildings. So the response of these buildings is correlated in a way. There's some dependency in the response of these buildings. This is also very common, for example, in the case of overpass bridges in highways, because generally we can see that there's pretty much like a copy and paste of the same bridge in different sites. So we would expect these bridges to have similar responses. The fact that this dependency exists doesn't necessarily mean that the buildings are going to have the same damage outcome. If we look at the pictures in the right, for example, we can see that in the picture below, all of the buildings collapsed, but in the picture above, just one of the buildings collapsed. So it's not like a matter of, yes, the buildings are similar, they are all going to have the same outcome. There's some sort of like randomness in there or some behavior in there, which is what we're trying to understand right now. What is this correlation? What causes this kind of behavior? So in order to understand better what are the implications of considering this variable into the analysis, we will look at this hypothetical case in which we have many buildings, all of them belonging to the same taxonomy in a region in a way that we have just one fragility function for all of them. If we also assume the hypothetical case that all of these buildings have a constant shaking, as if they were all located on the same site, they will all have a common probability of exceeding that damage state. Since we're considering just one damage state here, exceeding this damage state means resulting in damage. How usually this analysis is performed when no correlation is being accounted for. What is done is we sample a set of n times k independent uniform numbers to assign the damage state to each of the buildings, n being the number of buildings that we're analyzing, and k being the number of trials we're performing on the same scenario. So what is done is we just sample a random number between 0 and 1. And in this case, for example, that number is larger than p. So we say that the building is not damaged. We can do then another independent uniform number here. Well, this is what is a Monte Carlo simulation of a Bernoulli trial. A Bernoulli trial is a process in which we have two possible outcomes and one probability of observing that outcome. So that's why this is a Bernoulli trial. So, okay, as I was saying, we can generate then a second independent number. In this case, if it is lower than P. So we can say that the building is damaged, and we can do it again. Again, an independent number, and in this case, it is larger than P, so the building is not damaged. And we can repeat this many times until we have a table like this one that we can use to estimate losses, perform some statistics, determine the probability of exceeding a certain number of damaged buildings, etc. Now, if we want to consider a correlated damage case, we will need to sample now collectively all of the uniform numbers that are being used for each trial simultaneously in a way that they represent the correlated structure of damage that we expect this building to have. So, for example, here we will generate all of the random numbers for the buildings, and we will see that all three of them will result in not damage. And then we repeat again for all of the trials that we're running. And we get a table as the one that we got before. If we perform vertical statistics, we can see that for both cases, the amount of times of trials for which any building resulted in damage is going to tend to be proportional to P, to tend to be equal to P. And the same thing happens if we perform horizontal statistics for the uncorrelated case. However, for the correlated case, this doesn't happen. The proportion is not going to be equal to P, since we're going to observe more cases in which either more buildings collapse or less buildings collapse, or maybe all of them collapse because the response is not independent, it's correlated. Now, the question is, how can we estimate this correlation? How can we generate this set of uniform random numbers that represent the correlated structure of damage? So if you recall what I said before, the process of sampling each of these damage outcomes is a Bernoulli trial. So we could use the equation for estimating the correlation of Bernoulli trials, which is the one that I'm showing on the slide. It is a function of the marginal probability of damage, in this case of each of the buildings. So it's just the probability that comes from the fragility function, the probability of each building independently resulting in the damage state. And also it's a function of the joint probability of damage, which is the probability of both buildings resulting simultaneously in that particular damage state. So we believe that we can estimate that joint probability distribution from the results of nonlinear time history analysis, either from MSA, multiple stripe analysis, or IDA, with some implications from each of them that I will discuss later, if we use the same set of records for both buildings. We can then, as we do for determining the marginal probability of damage, we can count the cases for which a record caused both buildings to exceed the considered damage threshold, and in that way we can estimate that joint probability. I will talk a little bit later about the implications of using both methods, but that is like the general idea. So we decided to apply this in a case study in order to understand better what the implications of including this variable in the analysis would be. We performed then a regional assessment of mid-rise concrete frame buildings in the province of Caserta in southern Italy. We used a simulated portfolio of buildings, and we considered 3 different municipalities that share very similar high hazard, that are Gioia Sannitica, Piedimonte Matese, and Castello del Matese, all of them included in the Caserta province. We wanted this case study to be as realistic as possible, so we took the real exposure model for these 3 municipalities from the European seismic risk model, and we found that there are 62 mid-rise concrete frame buildings divided into 3 different taxonomies. The exposure model gives us all of the buildings that are in that municipality lumped into a common site. So we distributed all of them geographically using the spatial disaggregation algorithm developed by GEM based on the distribution of the population. So we would actually have like an assumed location, realistic location of where all of these could buildings be. We then use the built environments data design service to simulate the portfolio of buildings. It uses Monte Carlo simulation to sample the characteristics of the buildings from a real characterization of the buildings in the area. So for that, we use the characterization developed by Corlito and De Matteis in 2009 in a way that the simulated portfolio would also be as realistic as possible according to what we would expect the buildings in that municipalities to be. We then assign a random location to each of the buildings based on the spatially disaggregated exposure model that we had. So we will have for each location a specific model of the building that we're assuming to be in there. We perform a hazard analysis using a PSHA on OpenQuake in order to select records for the nonlinear time history analysis. We considered many return periods, and we selected 40 records for each of them using the conditional spectrum method. Since we needed to use the same set of records for all of the buildings, and we wanted these records to be representative for all of them, we chose as an IM the average spectral acceleration centered around the average period of all of the buildings. So we will be able to capture all the possible expected ranges in the response of all of the buildings. For the estimation of the fragility functions, we perform multiple stripe analysis on the full 3D models of the buildings, and then we fitted a log normal distribution using the maximum likelihood method. We considered two different damage states, light damage state that was defined as the case in which the PSD, the peak story drift, was larger than 1%, and then a collapse damage state that was defined as exceeding a PSD of 8%. So we derive fragility functions for all of the buildings in these two damage states. We then estimated the damage correlation with the equation and the methodology that I showed you before. As I told you, we could use the results of multiple stripe analysis or incremental dynamic analysis. Usually, MSA is preferred because we're using records that are hazard consistent for all of the hazard levels. However, this means that we will just have results for the obtained EDPs for some fixed stripes, intensity stripes, and the records are different for each of the stripes. So we cannot interpolate the results between different intensities. This means that we could only use MSA for estimating the correlations in cases in which all of the buildings have exactly the same intensity, and it coincides with one of the intensities used for the MSA. As an alternative, we can use IDA, which might have some bias in the results due to excessive scaling of the records, but this is something that always happens with IDA. But since here the same set of records is used for all of the intensities, and you progressively scale them until reaching collapse, you can actually interpolate the value of the EDP for any IM value. So that allows us to calculate the correlation for cases in which the intensities in both buildings are different. Since we're going to perform IDA, we wanted to also try what would be the impact in the results of using equivalent single degree of freedom oscillators instead of running the analysis on the full 3D model, because in that way we would reduce significantly the computational demand of the methodology in general. So we wanted to see what would also happen if we did that simplification. And also, in order to avoid having excessive scaling, we chose to use the same set of records that was selected for the 475-year return period for this analysis. So when we look at that intensity, the records used are exactly the same with the same scale factor, and the only difference in the results is going to come from the fact that one of the cases is using the SDOFs, the equivalent SDOFs, and the other one was performed on the full 3D models of the buildings. So considering that, we evaluated 3 different cases. The first one was a case of constant shaking with an intensity equal to 0.27 G, which corresponds to the intensity for the 475-year return period. This means, as I told you, that for this case, the only difference in the results is going to come from the use of the equivalent SDOFs. A second case with intensity higher than that one of 0.75 G that we used to see what were going to be the difference in the results when we also used IDA instead of MSA. And finally, the third case is based on a rupture scenario that we use just to see what were going to be the impacts in the results when on a more realistic case in which the intensities were different in all of the buildings. So as for the results of case one, we estimated the probability of exceeding a different number of damaged buildings that was calculated after performing 100,000 iterations of the same case. We counted how many times each of these number of buildings was exceeded. Like the number of damaged buildings was larger than the considered number of buildings. And that's how we obtained those curves. We can see that overall, the mean value is pretty much the same. The median value is pretty much the same. But there was a significant difference in the dispersion of the number of damaged buildings. As a consequence, the tails of the distribution are also different. And we if we ignore the correlation, which is what is usually done, we underestimate the probability of observing a large number of damaged buildings. So if we look, for example, at the probability of observing more than 40 damaged buildings from this scenario, if we ignore the damage correlation, it will be of around 7%. But if we consider the correlation with MSA, that in this case is with the full 3D models, it will be of 40%, and with the SDOFs, it will be 47%. We can see that using the SDOFs is slightly overestimating the impact of the correlation. But in any case, these results, even if using the SDOFs, are better than completely neglecting the correlation, which is what is usually done. Now for case two, the results are very similar. Let's say the impact of incorporating the correlation is pretty much the same. There is an increase in the probability of the tails. But in this case, the difference between the results of MSA and IDA are larger, and IDA is overestimating even more the probability of exceeding a certain number of damaged buildings. So if we look, for example, at the probability of having 35 damaged buildings, it goes from 1% if no correlation is considered to 31% if the correlation is calculated with MSA, and 40% if it is calculated with IDA. So there's a significant impact by incorporating the damage correlation. In any case, it's still better to consider the results with the IDA than completely neglecting the correlation. So now for case three, we consider this rupture. It was selected from the 475-year return period hazard. So because we know that for this level of intensities, the results from MSA and IDA are similar, so we wanted to decrease as much as we could the impact of using a different method. This corresponds to a scenario with a magnitude of 6.25 located at 5 kilometers from the points of mean coordinates of the buildings. We estimated for that scenario ground motion fields both considering and neglecting the spatial correlation. And we evaluated also applying both of the correlations. So if you see in the plot, the graph in black represents not considering any correlation. The one in red is considering the spatial correlation. The one in blue is only the damage correlation, and the one in green is considering all of the correlations. For this case in particular, we saw that spatial correlation has a very big impact, probably because all of our buildings are located too close from each other. So spatial correlation is very significant, but in any case, we can see that there's also an impact if we consider just the damage correlation by itself. It's important then to consider the correlations because let's say, for example, that the government of the province might say that they are prepared to fix, they can see this as the worst case scenario, and they can say that they are prepared to fix, for example, 45 buildings. And they want to know how likely is that that money is enough. So if no correlation is used, that probability of them having not enough money would be around 6%. So they might say that it's fine. But if we consider all of the correlations, that probability might increase to 36%, which maybe is not that fine anymore. So that is why it's important to consider also these variables, both the spatial correlation and the damage correlation, into these type of assessments. So as a conclusion from this study, we can say that incorporating the damage correlation significantly impacts the variability and shape of the distribution of number of damaged buildings. And this, including the variable, also allows us to have more accurate results for the in order to plan for mitigation strategies and for risk preparedness awareness. If you're interested in all of this work, we wrote a paper about it in which we're explaining everything in detail. You can find it by scanning the QR code that is on the slides. Now, let's talk about some of the considerations from this work in order to see how we can move forward. The first thing is that we found that for some cases, there were some negative correlation values, which it's a little weird because we're working with buildings that have very similar dynamic characteristics and behavior. So we should look further into why we're getting these negative values, if maybe it is an issue of that we need to use more records to quantify the general probability distribution or something like that. The second one is that this methodology was based on a building-specific approach in which we are assuming that we have nonlinear models of all of the buildings that we have in the region, which we know already is not very realistic. And we don't have these nonlinear models. So we would have to develop some mathematical models in order to estimate the correlation directly from some characteristics of the buildings. However, doing so can be very complicated because we need to guarantee that the correlation matrix that is obtained by calculating the correlation value with these models has to be positive semi-definite, which is a property of correlation matrices. That means that all of its eigenvalues are larger or equal than 0. And doing so from these correlation matrices that were obtained might be quite complicated. Also, we estimated the joint probability by considering that buildings that were experiencing the same intensity measure were also going to experience the same records. But in reality, this might not be the case. We might have two buildings with similar intensities, but that are located on opposite sides of the fault. So the properties of the record might be significantly different, and as a consequence, also the response of the building. And finally, for the case study, we only consider one damage state at a time. But in reality, you're considering many damage states. So in addition to having to develop a model for each of the considered damage states, you might also have to consider like an inter-damage state correlation, which will be what is the correlation of one building resulting in collapse and another building resulting in like a moderate damage. So now we will need to incorporate a lot of more models that will complicate significantly the problem in general. So for that, we consider using an EDP-based approach that is equivalent to the traditional damage state approach. In this approach, we will sample the EDP directly for each of the buildings from a given probabilistic model of the EDPs. And then after you sample the EDP value, according to which damage threshold was exceeded, you can assign the corresponding damage state for each of the buildings. Or you could also like estimate directly the losses with a story loss function, for example. By generating a set of correlated EDPs, we would intrinsically be considering all types of possible correlations between all of the different damage states. One of the drawbacks of this approach is that you need to have the probabilistic model of the EDPs. If you're deriving the fragility function from crowd analysis, for example, an intermediate step is developing a demand intensity model, which is a probabilistic model for the EDPs. So even though it might not be published, we know it exists. But for example, if you're working with empirical fragility functions, we don't have such a model, maybe for all of the taxonomies. But let's say that for now, we're going to consider that we have all of the demand intensity model for all of the buildings and all of the taxonomies. So now, in order to understand how we can deal with the problem, let's try to see what would be the ideal approach for estimating the correlation. So let's say that we know that the rupture that we're seeing on the slide is one of the ruptures that we need to consider on our scenario-based assessment. Let's say also that we have all of those sites, but specifically we have two buildings, building A and building B, that are located on site N and site M, respectively. And let's also consider that building A and building B are instrumented, so we can know when an earthquake occurs, what was the actual observed EDP in that building. So let's say that we had this rupture and we recorded what was the observed EDP on both of those buildings. Let's say now that we can have another realization of exactly the same rupture, and we could also record what was the observed EDP for that new realization of exactly the same rupture. If we repeat that many times, we will end up having a vector of observed EDPs on both of those buildings for that specific rupture that we're going to consider. We could estimate then the Pearson correlation of those two vectors, so we would have like a real calculation of what is the correlation in the EDPs of those two specific buildings located at those two specific sites for that specific rupture. We could repeat it then for all of the buildings, so we will have a correlation matrix for that of all of the buildings in our region for that rupture in particular, and then we could repeat it for all of our ruptures. In reality, this is not applicable because, first of all, we don't have many different realizations of the same rupture. We just have one. Also, we don't always have buildings that are instrumented, so we cannot estimate the correlation from that. So it's practically impossible to use this ideal approach. This is what it is ideal, why it is ideal. This is equivalent to what is done in spatial, of the problem of spatial correlation. Also in spatial correlation, we would like to have many observations of the intensities in our sites for the rupture we're considering. And how they deal with that in spatial correlation, because also in that case, they don't have those observations, is by relying on the ergodic assumption. What that does is considering that the residuals of IMs observed at different earthquakes, locations and times, the properties of these residuals are equivalent to the ones you would observe on many observations in time of given event of the two specific sites. So they rely on that assumption to develop mathematical models of the spatial correlation that are generally a function of distance. So to understand it better, what they think is that if we have two sites that are separated at a distance of 1 kilometer, the correlation in the residuals of the intensities of those two sites is going to be similar to the ones that you would have in many other sites that are also separated at 1 kilometer for many other earthquakes that happen in many other regions. So they use those observations of those earthquakes in other regions to estimate the correlations in the region that they would like to have it. So we could also rely on this assumption for the estimation of the correlation in the performance or in the EDPs. If you heard, I talked about the residuals of the intensities. So it's important to say what these residuals are, and they are a variable that represents how many standard deviations from the mean an observed value is. So in the case of EDPs, for example, we could estimate the EDPs from the demand intensity model using the equation that I'm showing on the slide that is divided into two portions. The first portion is a deterministic one, that is the median value obtained from the demand intensity model. So you just have the linear regression, the black line on the plot, that is a function of the intensity, so you know what is the expected EDP for given intensity, and that is a deterministic value. And then you have a probabilistic part, that is a function of the residual multiplied by the dispersion of the demand coming from the demand intensity model. So these residuals are usually considered as standard normal variables, so they have a mean equal to 0 and a standard deviation equal to 1. It is important to consider the correlation of the residuals instead of the correlation of the absolute values, because by correlating the absolute values, you can inflate the value of the correlation, because you might be observing 2 points that have very similar response because the mean is similar, because the expected value is similar, but not necessarily because the random part was similar. So by correlating the residuals directly, we are considering that. As I said before, then we could use the ergodic assumption to estimate correlation of the residuals of EDPs. For that, we could use real observations of real earthquakes that we might find. So for example, let's say that we have this earthquake and we have many stations that recorded that earthquake, and we have a specific record for each of those stations. So we also know what was the actual intensity in that site. If we take, for example, one building, let's say building A, and we have a nonlinear model of that building, we can perform a nonlinear time history analysis on that model for all of the records of all of the stations that we have for that rupture in particular. And in that way, we will have for each station a pair of intensity and observed EDP for that building.
Yeah.
We can then use that, if we have then a demand intensity model of that building and we develop a demand intensity model, we could calculate what is the residual at each of those stations. So we would end up having a map for a specific earthquake of what was the residual of that building. And we can then use some geostatistical tools to derive, for example, in that case, model that is a function of distance. So we will know if we have the same building, but we have it located on different sites at certain distance, what will be the correlation of that same building. If we consider now another building, and we had two buildings, then we could estimate the correlation in the residuals of these two buildings. But now the equation should be not only a function of the distance, but also, or we have many buildings, a function of the structural properties of the buildings. So the problem of fitting a model becomes way more tricky than in the case of special correlation, and more things need to be considered. So I will discuss that briefly later, but let's say for now that this is like the general approach you could use to develop these correlation models. We wanted then to try with an example to see what will be the implications of using this EDP correlated based approach. So for that, we took a simulated portfolio of 80 buildings belonging, all of them, they are Turkish buildings with high ductility that were constructed between the year 2000 and 2018. They were also obtained with the BED design service, the same that I used before, but with some modifications that were performed specifically for Turkish buildings by Serkan, which is another PhD student here. We then performed a cloud analysis to all of these 80 buildings on equivalent SDOF oscillators, nonlinear oscillators, and we used 500 records that were selected with an unconditional approach. We scaled them two more times to obtain more points in the nonlinear range. And in that way, we derived building-specific demand intensity models for each of the buildings. I'm showing you there, for example, the demand intensity model for building 50. And we did that for all of them. Then we combined all of the demand intensity models to obtain a demand intensity model for the whole taxonomy that accounts both for the intra-building variability, that in this case is just the record-to-record variability because we didn't consider any other source of variability, and the inter-building variability to account for also for how different could the results be since there's variability in the characteristics of the buildings. Something important that must be noted is that demand intensity models are conditioned on the non-collapse of the buildings. So the regression of the mean was done only excluding the cases that we assumed were collapsed. We defined in this case collapse as exceeding a PSD of 5%. So it is conditioned on the fact that the PSD is lower than 5%. We wanted to check how, let's do some checks on the obtained taxonomy demand intensity model. So first we checked that the residuals that were obtained for all of the buildings and all of the records used in the cloud analysis really did follow our standard normal distribution, as we can see on the left. The mean is very close to 0. The standard deviation is very close to 1. So let's say that is correct. And we also wanted to check if there was some sort of bias in the results due to the magnitude of the event, which is a check on the right. And we didn't find any clear evidence of any bias due to the magnitude. So let's say that for now, we are considering the demand intensity models are appropriate. As I said before, these demand intensity models are conditional on non-collapse, so the collapse cases must be considered separately. For that, we developed a collapse fragility function for each of the buildings specifically. We fitted the equation that I'm showing on we did a logistic regression to fit the A0 and A1 parameters from the equation that I'm showing on the slide to the data that resulted in collapse from the cloud analysis. And with that equation, we found the parameters of the fragility function. And also in this case, we combined all of them into a taxonomy one, considering both the intra and inter-building variability. We did the assessment then for the Chichi event that happened in 1999 and had a magnitude of 7.3. Since this event has many, many records, like 400 records of the real experience time history, we perform a nonlinear time history analysis then on all of our 80 buildings in all of these records. And in that way, we could obtain then the residual EDP, and in this case is PSD, for all of our buildings. So for example, these maps show the residuals for the two buildings, building 17 and building 50. And these are the sort of residuals that we could use to derive the mathematical models of the correlation. In this case, what we did was we just assigned to each of those stations a random building in a way that we could have like a real simulated, but real damage situation. So we will know for each of the buildings located at each of the stations what was the actual observed PSD. We consider then for the assessment these correlation models. For the collapse cases, we consider one that is a function of the Euclidean distance between the buildings and the absolute difference in the periods of vibration of the buildings. And for the non-collapse cases, we consider also one that has these two variables, one that has these two variables in addition to the absolute difference in the yield acceleration of the buildings, and one that is just a function of the absolute difference in the period and the absolute difference in the yield acceleration. I will not discuss right now where these models come from. Let's just say that these are the sort of models that we would expect to use in this type of assessments. And these models guarantee that the resulting correlation matrix is positive semi-definite. So they satisfy that condition. We performed then the damage estimation. We use the real ground motion field of the Chichi earthquake. So here we're not considering any source of variability in the ground motion fields. We're using the real intensities that were recorded for that event. And we are just doing the assessment for the damage of outcome of the buildings. So we consider a damage threshold of 0.5%. So what we did was just for the real damage, like that we are assuming, like I told you before, we consider a random building located at each of the stations. We just checked how many of those buildings were exceeding a PSD of 0.5, and that's what we're considering as the real damage case. That is, we found that was 75 buildings. Then for the assessment, we just sampled the EDPs of all of the buildings and the collapse cases of all of the buildings, and we're estimating that the probability of exceedance, as we did on the first case study. So we can see that the probability of exceeding the real damage that we observed with no correlation is considered is of 0.25%, which is very low. It's almost, we will be pretty much saying that observing the real damage was impossible. But if we consider the HT or the HTS correlation models, that probability increases to 20%. So the real observed damage becomes more likely to occur. And if we consider the TS model, it increases to 30%, which is even higher. However, we can see that the TS model is very correlated because we're not considering any decreasing in the correlation from the distance of the buildings. So by this, we can see how important it is to consider the damage correlations. The assessments become more consistent with the assessment becomes more consistent with what we actually observed there. And in that way, we can have more realistic assessments by incorporating the damage correlation. So the ongoing work, what we have to do right now is actually develop the models for the EDP residuals or the collapse cases, for example. Again, we need to guarantee that these models yield to a positive semi-definite correlation matrix. And right now we're testing the use of Bayesian inference to fit these models, considering multiple variables. As a spoiler, the models I used for the assessment actually come from some testings we're doing right now with this Bayesian inference. So they don't come from nowhere, but I didn't want to talk right now about how we develop them because it's still ongoing. So we're still tweaking some things. As a conclusion then, incorporating structure damage correlation in seismic risk assessments really impacts the probability of observing high impact damage. Due to the complexity of the problem, it might be better to incorporate this variable with an EDP-based approach instead of the traditional damage-based approach. We need to develop mathematical models to do it, and they can be developed with an analogous way to what is done for spatial correlation. And some future work then should focus on the development of these specific models. So that will be all. Thank you all for your attention. I know this topic is a little complex. I hope that I was able to explain it in a way that you could understand it. So now it's time if you have some questions or you want to discuss something.